All right, class. So in this unit, we're going to start a new unit now. So in this unit, we're going to be looking at exponential functions and logarithmic functions. So to introduce the first lesson in the unit, we're going to talk about exponential growth. In the second lesson, we'll talk about exponential decay. So in this lesson, we want to be able to graph exponential functions that model growth, and we want to be able to apply this model to applications which involve some kind of growth. All right, so those are what we want to do. We want to be able to graph, and we want to be able to determine characteristics of that graph, such as X-intercepts, Y-intercepts, domain, range, etc. And then we want to use some applications. All right, so let's first talk about introduce exponential functions. So an exponential function has this generic equation. All right, remember that like if you had like 2 to the second or 2 to the third power, then 3 is your exponent. And 2 is what we call our base. So in this case, b is our base. All right, and then so h here translates the graph horizontally, left or right. So it translated left or right, but if h is positive here, that means that this sign here is going to be negative, and we know that if it's negative on the inside right here, that means that it's going right. So if it's left, then that means h would be negative, because two negatives make a positive. So if h was like -2, then we would have minus -2, which makes +2. And we know that if it's a +2 on the inside, like which is here, then that means it's going left. So therefore, if h is negative, it's going left. And if it's positive, then it's going right, okay? So don't get confused with that. Negative because two negatives here make a positive. Right because a negative and a positive makes a negative. And we know that negative is right. For k, here, if k is positive, then this sign is positive, which means it's going up. If k is negative, then this is negative, which means it's going down. So, so it's going down if k is negative, and it's going up if k is positive. Okay, so that takes care of the hk. Now for the a, if a is bigger than 0, so if a is positive, then means the graph is going up. So the graph opens up, and if a is negative, the graph opens down. So in this case, if a is greater than 1, or so if, let's just say if the absolute, so if a is greater than, so if the absolute value of a is greater than 1, we're going to say absolute value. And the reason we're going to say that is because you can have a negative value that's greater, that's, big, okay? So like it could be, as long as the absolute value is greater than 1, then you can use this condition. All right, so make sure you include the absolute value. I forgot to include that there. So if the absolute value is bigger than 1, that means that the graph has a vertical stretch, okay? So vertical stretch by a factor of a. So if we had, like 3 times 2 to the x, for example, then that 3 is your a. That 3 is bigger than 1, so that means that it's going to be a vertical stretch by a factor of 3. Okay, if the absolute value a is less than 1, the graph has a vertical compression by a factor of a. And if c is less than 0, so c is this guy here, if that's less than 0, which means it's negative, so so we're just going to say if it's negative, that means that the graph is a reflection about, in this case, about the x-axis. I'm sorry, about the y-axis. And then if the a is negative, then it's a reflection about the x-axis. Okay, that's just a little review of transformations. Remember, these are all transformations. So like if you want to go back and review those, this is sort of like a mini review of that. So yeah, all of these are transformations. So let me just write that down. So that way you can refer to that and review that if you need to. Now, if absolute value of c is greater than 1, that means that we have horizontal. Remember, it reverses. So if you're on the inside and it's bigger than 1, and normally you would think it's a stretch, but really it's a compression. So it kind of reverses when you're dealing with the inside with the X stuff. All right, so horizontal compression by a factor of 1 over c. So like if you had, I don't know, let's say you had 3 times 2 to the 5x. In this case, the 3 is vertical stretch. The 5 is a horizontal compression by a factor of 1 over 5, 1 over c. Okay. If the absolute value of c is less than 1, then it's stretch. So it's a horizontal stretch by a factor of 1 over c. All right, so that's just a quick review of transformations and how you do that with exponentials. So let's look at a couple examples. So for number 1, we're looking at we want to determine which direction it shifts. So basically, we're going to just explain what the transformations are. So for this guy, we have the base is 4, so that doesn't do anything to the graph. It's just 4, and then so here the h is equal to 3, so that means that it shifted to the right 3. Okay, so let's write out what the parent function of this is so that we can kind of review that. Remember, the parent function is the original function that doesn't have any transformations on it. So in this example, the transformation is the parent function is y equals 4 to the x power. That's the base bare bones function that is not transformed at all. So in this example, if you were to take this parent function and transform it, then this means that you would shift to the right 3 units, and you would shift up 1 unit. Okay, so in this example, h is 3. Which means that this is negative, so that means you're shifting right. So you can think of it that way. If it's negative here, then it's shift right. So you can also think of it that way. And then this is going up, so that's 1, going up 1. It's positive. All right, now the parent function for here is also y equals 4 to the x. So you're going to take the parent function, you're going to shift it left 2. And the reason you do left 2 is because you have a positive on the inside, or you can think of it as h is negative 2, same thing. In this case, your k is negative 7, or this number is negative, so you can think of it as a shift down 7 units. All right, and that's how you do that. So it's really not that bad. You just gotta recall your transformation rules. All right, so we're going to go ahead and graph 2 to the x power. So in order to graph this, we're going to set up the table, which is already provided for you. So we're going to choose some values. So let's choose negative 2, negative 1, 0, 1, and 2. Okay, so we're going to show our calculations here. Remember, you got to remember the exponent properties. So what happens if you get a negative exponent? So if you plugged in negative 2 into x here, then you'd have 2 to the negative 2. Remember that negative means flip and forget. So that means you're going to flip it down to the bottom and forget it. So you're going to do a reciprocal here. So you're going to do 1. So 1 flips on top, 2 flips on the bottom. So you got 1 over 2 to the then forget. So flip and forget. So it's going to be positive 2 power. And then 2 squared is 4. So this is really 1 over 4. So this is 1 over 4. Now we're going to do 2 to the negative 1 power, which is flip and forget. 1 over 2 to the first, which is 1 over 2. Now we have 2 to the 0 power, which is equal to 1. So we're going to go ahead and write that down here. 2 to the first is 2. 2 to the second is 4. Now we're going to go ahead and plot the points. So we have negative 2, 1/4. 1/4 is very small. It's around there. Negative 1 and 1/2. 0, 1, 1, 2, 2, 4. All right, so In this case, if you're going in the negative direction, it's only getting smaller and smaller, but it's never actually getting to 0, if you notice. So we can go ahead and draw the graph. So it's getting closer and closer, but it's never actually touching the x-axis, all right? And then it's growing, 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 and it's continuously growing. All right, so that's how our graph looks like. That's how an exponential function looks like. So most exponential functions will look like that, and this is how it looks like if it's positive. If it's negative, then it will kind of look like that. It will be a reflection about the x-axis. Okay, so that's how it looks like if it opens down. So just to show you. All right, so now let's do the x-intercept. So since this approaches the x-axis but never actually crosses it, that means that there is no x-intercept. Okay, so there is none. All right, so for this guy, since there is no x-intercept, that means that this is a horizontal asymptote. So in this example, for exponential function, the horizontal asymptote is y equals 0. So this is the horizontal asymptote. Let me do that in red. So y equals 0, and that is our horizontal asymptote. So we're going to write that here. All right, so now let's look at y-intercept. So y-intercept is where the graph crosses the y-axis, which, the graph crosses the y-axis there, right there. So that's our y-intercept, which is at a value of where y is equal to 1. So the y-intercept is y equal to 1, all right? Or you can write the coordinates 0, 1, same thing, all right? The domain. So the domain is where x is valid in the graph. So here we have all the x values in the graph. If you notice that if you continue graph it, it goes forever in the x, and the negative, forever in the positive. So that means it's all real numbers. So we're going to say all real numbers. You can use that R, or you can just type in, or you can just write in all real numbers. Or you can use negative infinity to positive infinity, which means all negative numbers, all positive numbers. Oops, let me get this out of here. Okay, so now we're going to do the intervals of increase and decrease. So in order to do that, we want to figure out where it increases or decreases. So in this case, it doesn't decrease at all. It just increases. So which means that we're only going to have one interval. So this graph increases. So it increases, and it increases from all x values. So notice that if you're going from left to right here, so it increases from negative infinity to positive infinity. So it increases from left to right for all numbers. So from negative infinity to positive infinity. I want you to get used to doing that, to writing those intervals of increase and decrease. All right, so for the range is basically all the y's. So in this case, the smallest that y can be is not even 0. So y can't even be 0. So y can only be greater than 0. So we're going to say y is greater than 0. It can't equal 0, but it can be greater than. And for the end behavior, in this case, in this example, we have, so we're going to do as, I'll do it down here because we need more room. So as x approaches infinity, y approaches. So as x gets bigger in the positive direction, then that means as x gets bigger here, that means y is going positive. Y is going up, which means it's going to positive infinity. All right, and then as x approaches negative infinity, y approaches. So as x gets more and more negative on the left side, the graph is actually approaching, notice that the graph is approaching the red, right? So that means that y is approaching 0. Okay, so that's a little tricky. See, the graph is actually, so as x goes this way, the graph is approaching that, right? So that means it's approaching 0. All right, so let me erase that now. All right, so that's how you do those guys. So let me do another practice problem for you guys. All right, so again, now we have a graph. This time we have a transformation here. So we're going to go ahead and you pretty much use our same numbers, since it's not going to change our results except for the 1/3. So in this case, if you were to do the -2, you would have 1/3 times 2 to the -2, 1/3 times 1/4. Because remember, it's 1/2 squared, which is 4. All right, so let me write it out because I know you guys will want to see that. So we got 1/3 and then 1/4. So this is where you do the flip and forget, and you get 1/12. All right, so now for the -1, 1/3, 2 to the -1. So 1/3, flip it, 1/2 to the 1, which is 1/6. Now we're going to do 1/3 times 2 to the 0. Anything to the 0 power is 1. So then 1 times 1/3 is 1/3. Okay, now we got 1/3 times 2 to the first power, which is 1/3 times 2, which remember 2 times 1 is 2, so it's 2/3. Now we got, so let me show you on here. So now we got 1/3 times 2 to the second. 2 to the second is 4, so that gives us 4/3. 4 times 1 is 4. All right, so now we have ourselves 4/3. Now I'm going to graph it. These are really small numbers, so I can only go so far with my pen. So we're going to do the best we can. So -2 and really small. -1, really small. 0 and 1/3, again, really small. We're going to do the best we can. And then 1 and 2/3. So now these are so small. So like, let's do it again. Let's try to do the best we can. This is very close to 0. This is even closer to this. I mean, this is a little bit above it. This one's a little bit above it. Then we have 1 and 2/3, which is a little bit above it. Then it's 2 and 4/3. So 4/3 is a little over 1. 1 and 1/3. So that's around here. All right. So it is growing. It's just growing more slowly. It looks like it's growing more slowly here. All right. But it is growing. All right, so it's trying to approach the x-axis, which in this case is our horizontal asymptote. Okay, so our horizontal asymptote is y equal to 0. And it's growing slowly. So notice what's happening is that this graph is actually compressed, because if you compare this to the previous graph, the previous graph is going up pretty fast, whereas this one is not going up as fast. It's going up eventually, but then, you know, it just takes a while for it to get there. So that means that this is and you can tell that the 1/3 there shifts, so it's a vertical compression. by factor of 1/3. So which we can tell it's being pressed down, so it's smaller than the other one. All right, so now the x-intercept, again, there's none. Y-intercept, this time the y-intercept is, here. Remember, the y-intercept is where x is equal to 0. So our y-intercept is y equals 1/3. That's where it crosses the, the x-axis. That's our y-intercept there, which, corresponds to that point there. And then the asymptote is y equals 0. The domain, again, is all real numbers, but I'm going to write negative infinity to positive infinity. Intervals of increase and decrease, again, it's only increasing, and it's increasing from negative numbers to positive numbers. Range, again, it's y is greater than 0. The graph goes above the x-axis. And then the end behavior as x approaches positive infinity. So as x goes to the right, the graph is going up and up. So y approaches positive infinity. As x approaches negative infinity, so as x goes negative, the graph is doing this motion and is approaching y is approaching 0. All right, so that's the end behavior, and that's it for that example. So let's do another one. Okay, so we have a couple transformations here. So notice that we have the 3 there, we have the 5, and we have the 4. So we have 3 transformations. So I'm going to try to write them down here. So we have a vertical stretch, by a factor of 3. We have a shift left, and it's left because it's positive here, like the actual sign here is positive, but the h is negative. So shift left 5 units. And then we want to shift down 4 units. All right, so I changed sorry guys, I changed the graph a little bit so that I have more room for this graph. All right, so in this case, we're gonna continue with the same values that we chose for x. Actually, no, we don't want to choose those values for x. And the reason why we don't want to choose the same values is because now we have a plus 5 there, right? So remember that we wanted it to be 2 to the negative 2. We wanted it to be 2 to the negative 1, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. So in this case, the only way we can get negative 2 here is if x is negative 7. Okay, so if x were negative 7, then then you would have here, you would have 2 to the negative 7 plus 5, and that will give you 2 to the negative 2. If x were negative 6, then that would give us 2 to the negative 1. If x were 0, or if x were negative 5, then that would give us 2 to the 0. If x were negative 4, that would give us 2 to the first, and so on. And and if x were negative 3, it would give us 2 to the second. Okay, so and that's how we get those values. So now if we plug it in, so I'll show you over here. So let's do negative 7. So we got 3 times 2 to the negative 7 plus 5, and then minus 4. So we have 3 times 2 to the negative 2 minus 4. Again, that's 3 times 1 over 4 minus 4, which is 3 over 4 minus 4. So 3 times 1 is 3. So this is 3 over 4, which is 0.75 on the calculator. And if you subtract those, you get negative 3.25. I'm going to write it as a decimal just for ease of use here. All right, so now we got 3 times 2 to the negative 6 plus 5. 3 times 2 to the negative 1. I forgot the minus 4. Minus 4. And then minus 4 here. So we got 3 times 1 over 2, which is 3 times 1 over 2 is 3 over 2. Minus 4. And then we got 1.5 minus 4. This will give you negative 2.5 on the calculator. If you were to do it. I just did it mentally, but you can do it on the calculator in this example. So 3 times 2 to the negative 5 plus 5 minus 4. So we got 3 times 2 to the 0 is 2 to the 0 is 1. 1 times 3 is 3. 3 minus 4 is negative 1. Now we're going to look at negative 4. 3 times 2 to the negative 4 plus 5. So we got 3 times 2 to the 1. 3 times 2 is 6. Oh, and I forgot to do minus 4. So minus 4 would be 2. So minus 4 will give us 2. So change that to a 2. All right, and lastly, we got 3 times 2 to the negative 3 plus 5 minus 4. So we got 3 times 2 to the second minus 4. 2 squared is 4. 3 times 4 is 12. 12 minus 4 is 8. So put the 8 there. All right, so we got negative 7 and negative 3.25. 1, 2, 3, negative 3.25. Negative 6, negative 2.5. Negative 5, negative 1. Negative 4 and 2. Negative 3 and 8. Okay, so again, notice the negative 3.25. So this is actually approaching negative 4. How do I know that? Well, the easy way to figure it out is use this shift number. The one that's on the outside, that'll tell you your asymptote. Okay, so your asymptote is going to be given by, y equals negative 4. Okay, so that basically is your HA. So that's a good way to remember. So then that means I know that my HA is around negative 4. All right, so that means that this is going to approach. It's going to get smaller and smaller. Trying to approach. Okay, there you go. So it's trying to approach the HA. So again, we have oops. Okay, so we have y equal to negative 4. And again, the easy way to tell is use this vertical shift. Use the k value to help you with your HA. So for HA, use the k value. That actually does help you find your k. All right, so now let's do the X-Intercept. So again, this one actually has an X-Intercept, so it will no longer be none because it's crossing here. However, we will not learn how to determine X-Intercepts until later in the chapter. So we're not going to do X-Intercepts for this yet, okay? So we're going to cross this out because we're not going to do that yet. But you just got to know that there is an X-Intercept, okay? The X-Intercept is around there. So X-Intercept is there, but at this point, we haven't learned how to determine what that X-Intercept is, without using technology, that is. All right, so we're going to leave it there and just cross that out. So with a Y-intercept, we can find that out. So remember, the y-intercept is when x is equal to 0. So we're going to plug in 0 in for x, okay, and figure out what that is. So let's do that. I'm going to do that up here. Let me do that up here so we have enough room. So x is 0. So we got 3 times 2 to the 0 plus 5 minus 4. So we got 3 times 2 to the 5th minus 4. So 2 to the 5th is 32. So we got 3 times 32 minus 4. So 3 times 32 is 96. 96 minus 4 is 92. So again, it's a pretty big value. However, that does make sense because it's not even crossing here. It's not going to cross until way above, which we can tell. Like if we continue this graph, it'll eventually cross the y-axis, but it won't be until it reaches 92. All right, so for the asymptote, there's only the one, so y equals -4. The domain is all real numbers, or -infinity to +infinity. Intervals of increase and decrease. So that means as we go from left to right, the graph is increasing, and it's increasing from all negative numbers on the left side to the all positive numbers on the right side. The range, now the smallest that y can be is greater than -4. Like y can't even be -4. So we have to make y greater than -4, but it cannot equal because it can't cross. For end behavior, as x gets bigger and bigger in the positive direction, the graph is going like this. It's going up and up. So it's going to +infinity. As x approaches -infinity, so as x is going to the left, then it's approaching -4. So y is approaching -4. Is approaching the red. Okay, I'm going to erase that. All right, so let's do yet another example. So we know, or not a graph example, just a transformation example. So what is the parent function of g of x equals -3 raised to the 2x minus 6 minus 7? All right, so we're going to list all the transformations. So in here, remember the base is 3, so that's the base. All right, the a is that. Okay, so that's the a. So a is -1 in this case. A is -1. So since a is -1, so a is less than 0, that means that we have a reflection about the x-axis. For the 2 here, the 2 on the top means that it's going to be reflected. Oh, not reflect, I'm sorry. It's going to be stretched or compressed, depending on, the number, right? So before we do this, I'm going to, every time you have a number in front of x, you want to factor that out like that, so that you can find out what your h is. So when we factor out a 2 there, we get x minus 3 and then minus 7. So every time you have a number in front of x, pull that out and factor it out and then figure out what the inside is. All right, so our c is 2, and remember, if c is greater than 1, that means it's a horizontal compression. So this is horizontal compression by a factor of 1 over c, which c is 2, so it's 1 over 2. All right, now we have a shift. Now we can tell what the h is. The h is +3, which means that, this is going to shift right. Or you can think of it as this is negative on the inside, so it's right. So shift right 3. And this is negative on the outside, so shift down 7. All right, so those are the 4 transformations in that. I wanted to do this example because you need to know how to pull out that 2, because they will be able to. They will ask you examples with a number in front of x, like for exponential graphs. So I want you to know what that does. All right. So now we're looking at exponential growth. So how do we apply this stuff essentially? So so how do we apply this in terms of growth factor? So when a real life quantity increases by a fixed percent each year, the amount y after t years can be modeled by the following equation. So this is our equation. This is the generic equation whenever you have growth in applications. So A is what you start out with. 1 stands for 100%, and R is your percent of growth. So like in this case, if you had 5% growth, then this will be 1 plus 0.05. You want to write it as a decimal, okay? So 5% would be written as 0.05. So then 1 plus 0.05 will be 1.05. So if this was 1 plus 0.05, then that would be 1.05. And that indicates that it's a 5% growth. Or you can think of it as a 105% increase, which means 5% growth. All right, so we're going to use that model for the following problem. So in 1990, the cost of tuition at Faber College was $4,300. During the next 8 years, the tuition rose 4% each year. So this is a classic example of exponential growth. The tuition is rising, and this is something that is applicable to even today. Tuition generally tends to rise, and we want to figure out, we want to predict how much it will be, later down the road. So we're going to use the model. So we're going to write down the model. So we got y equals, so A is the initial amount. So A is 4,300 here. So we have 4,300 times 1 plus, so now we got 4%, that's our R. So that's 0.04. So we got 0.04 raised to the t. All right, that's our model. And I'm going to simplify that. So that simplifies to 4,300, 1.04 to the t power. All right, so that's our final model. And notice that this is an exponential. That's our base. That's our exponent. And then that makes it vertically stretched by 4,300. So now we're going to graph it. So in order to graph it, we kind of need to plug in points into it. So we're going to, plug in for, 1, 2, 3, 4, 5, and for 0. So if we plug in for 0, and I'm going to do this on the calculator, by the way. So this will be, you guys will need to have a calculator for this part. But for 0, you don't need a calculator. 1.04 to the 0, anything to the 0 power is 1. 1 times 4,300 is 4,300. All right, so when it's 0, you got about 4,300. So that's around there. All right, so I'm going to plug in now 1 for t, so 1.04 to the first, 1.04 to the second, third, fourth, fifth, and then I'm going to times it by 4,300 and get my numbers. All right, so I'll write down those numbers and I'll be back. All right, so there's the value. So I plugged it into the calculator for all the powers. And so now we're going to graph it. So then for 1, we have 4472. So that's a little bit below 4,500. For 2, we have a little bit above 4,500. Oops, this dot needs to be to the right more. For 2, yeah, it's going to be about a little bit above it. For 3, it's going to be 4,800, so not quite 5,000. 4 is going to be a little bit above 5,000, and 5 a little bit above that. All right, so we're going to go ahead and graph this as the best we can.
So it's growing pretty slowly. Notice that the growth is really slow, and that's because 1.04 is a very small number for an exponent, like for a base of an exponent. Like you notice that it's not increasing very fast, and these are in years, and so this is typical. Like if 4% is not that much, but after like 10, 15 years, it adds up, right? So right now at 5 years, we're at $5,232. Up from 4,300. So that it does make a difference, 4%, although it's not as high, as most exponential functions are, but it's still increasing nonetheless. So it's not a good thing that it's increasing, for the student, of course. All right. So now we're going to look at another application. This is the last application we'll use, and notice that the formula is very similar. And this is interest rate and interest. So this is, a very applicable application to a lot of things in banking, and whenever you, get a house and you want to pay a mortgage, all that stuff. So this is very applicable to that, to life in general. So, and this is how they calculate the interest that you need to pay back when you borrow money. So A is the amount of interest that you're being charged. So actually, this is the amount in the account, the total amount, sorry. So this is the total amount, which it says it in there, that's the total amount. T is the number of years, N is the number of times it compounds. So the number of times that they're basically doing the interest, like applying the interest. And then R is the interest rate. Remember that the interest rate is a decimal, okay? All right, so let's use that example. So, and P is the principal, so which is the initial amount. Oh, it says it all in here, so I'm not going to write it, but it's all there. All right, so now you deposit $1,500 into an account that pays 6% annual interest. Okay, so in this case, you're not borrowing, but you're making the interest. So you're letting the bank borrow money from you, and and then they're being charged interest. So that means you're getting that money added to your account. So in this case, you're depositing $1,500. That's your principal, and then you're being paid 6%. So that's R, which is 0.06. Convert that to a decimal, just move the decimal place twice to the left. Find the balance after 3 years if the interest is compounded. So we want the time is 3. Okay, so if it's compounded annually, that means the N is 1. It's only being applied once, like the interest is being applied once. For semi-annually, the interest is being applied twice, but it's being split. So it's not like they're doing 4% twice. The 4% is for the whole year because it's an annual rate. But they're just splitting it into 2 pieces. So 2% the first time and then 2% the next time. So it's being split by 2. So here it's compounded 2. And then for the quarterly, it's being compounded 4 times. So instead of doing it 6%, if it was 4%, for example, then it would be 1% each time they apply the interest. So they'll do it 4 times in the year, and it'll be 1% each time. So that's what that stands for. That's what that means. So all right, so for n equals 1, we have A equals 1,500, 1 plus 0.06 divided by 1 in this case. So we're just plugging in the numbers. N is 1, R is 0.06, N is 1, so 1 times T, 1 times 3. And then we get that number. So I'll get that number in a little bit, and then I'll put it in there. But first, let me just go ahead and do B. So these are calculator heavy problems. You're going to need a calculator for this stuff. So 1,500, we got 1 plus 0.06 divided by 2. And then we have 2 times 3. So in this case, since you're doing it for 3 years, you're doing it semi-annually, that means that they're applying interest 6 times. They're compounding it 6 times, a total of 6 times. Since 2 times every year for 3 years. So we'll get that number. We'll get that on the calculator.
1 plus 0.06 divided by 4, and then 4 times 3. So the only thing that changes is the n. All right, so we'll get those numbers, and I'll write those numbers down. All right, so these are the numbers. So I went ahead and plugged it in the calculator, and notice that when you do it annually, you get this amount, and then when you compound multiple times, you get even more. But after a little bit, so if you do it quarterly, and then you do it 8 times, 10 times compounded, and so on, eventually you'll start leveling out. It won't increase that much more. So notice that it's only a $2 change if you go from compounding it twice to 4 times. But it's still something, in terms of money, because this is the money that's going to be in your account. So, which is pretty good after 3 years, and that's how much you'll get. You'll get over $2,000 back. So 6% is actually pretty good annual interest rate. And nowadays it's very hard to get that. It's very hard to get 6%. Most, the highest you can get in normal banks is about 2%. So that's pretty high. All right. And that is it, guys. So, so there's applications. So just know how to do the calculations here and know how to do the transformations and the graphs, and you should be set. All right, guys, take care.